Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp for Science for the Public, and we welcome you to the Public Science Lecture Series sponsored this year at Boston University College of Arts and Sciences. And tonight we have a second coming from a presenter who did another program for us back in the fall, which I'm going to explain in just a minute. Dr. Gang Chen is currently the Carl Richard Soderberg Professor of Power Engineering at Massachusetts Institute of Technology. He's the director of the Solid State Solar Thermal Energy Conversion Center, Department of Energy Frontier Research Center. He's a leading force internationally in the field of nanoscale energy, and he's published extensively in the area of nanoscale energy transport and conversion and nanoscale heat transfer. Professor Chen has received many awards, among them the National Science Foundation Young Investigator Award, the R&D 100 Award, the MIT McDonald Award for Excellence in Mentoring and Advising, and a number of others. He's a fellow of the American Association for the Advancement of Science and other prestigious science organizations. And he's the chair of the American Society of Mechanical Engineers. Also, he's the editor of several major professional publications. Professor Chen's appearance here tonight is the result of an earlier appearance in the fall at our other Science for the Public program, Contemporary Science Issues and Innovations, which we record at the Belmont Media Center Community TV. There was such a huge response to that program that I asked Dr. Chen if he would do an encore in the lecture series here at Boston University where we can accommodate an audience. He said yes, not realizing that we would have to schedule this appearance on Valentine's Day. I hope he and his wife will forgive me, and in any case, he's being a very good sport. You're going to hear a wonderful discussion of a very significant development in energy production. We don't get to hear much about solar thermoelectric generators, also known as STEGs. And Dr. Chen's innovation is widely viewed as a breakthrough using an elegant nanotechnology that produces both heat and electrical power simply, efficiently, and inexpensively. You'll hear how popular these STEGs are becoming in other countries, and you'll enjoy the opportunity to hear and see a prototype and to talk to Professor Chen. It's a great honor to welcome one of today's foremost innovators in energy technology, Professor Gang Chen.
Happy Valentine's Day. My wife was happy I'm here, actually. So it's a really great pleasure to come back. I made sure that I bought some flower last night. So today, I would like to share with you the research we're doing in the solar energy conversion into electricity. I call it the third way. I hope I'll be able to do justice to say why, explain why it's called the third way. But my plan is to actually start with a bigger picture. What are the challenges that we're facing, and then give a review of the current way of converting solar energy into electricity. Then I'll explain the solar thermoelectric generators and also touch upon some other potentials of the thermoelectric energy conversion technology. So let me start with the challenge we're facing. And right now, we have a population about 6.5, 6.6 billion in the world. And you can see that the projection is by 2050, the population will grow into 8.9 billion. And keeping in mind, this is about the size of China and India combined. So we have a huge population growth down in the future, and we need to feed this population with food and energy. And if we look at the energy consumption per capita, and here is the income in constant dollar, and China is here, India is here, and US is here. That's the energy consumption per year. So you clearly, as people improve their income and livelihood, their demand for energy increases. And that's why even with this 2 some billion population increase, the energy demand will be even much higher down the stream. And the projection is right now we're about 40 terawatts of annual energy consumption, and by 2050 we need about 25 to 30 terawatt. And 1 terawatt is 12 zeros of 1 watt, so 10 to the 12th power. And if you go to calculate, essentially almost every day, if we build one power plant that typically is about 1 gigawatt continuously over the next 38 years, we are about 12 terawatt. So that's the challenge. And the energy demand is very high, and how we can do this economically and sustainably. And if we look at the current energy usage, is mostly through the fossil fuels. And we burn oil, gas, coals, and the renewable energy actually most come from hydropower. So these fossil fuels release CO2 to the atmosphere, and that creates big challenge in terms of the temperature, global warming. And this is a very interesting geology facts. So you can say that about every 100,000 years, the Earth's temperature here, the Earth's temperature fluctuate from positive to negative. So we got the ice age, and then say it warm up. And this is a fluctuation is closely related to the CO2 content in the atmosphere. And those, of course, are natural event, but now with our usage of the fossil fuels, the CO2 content in the atmosphere is increasing very rapidly. Here you can say this is the CO2 content, and here 2000, and over the last 100 years, the CO2 content is definitely associated with our human activities and the fossil fuels. So those environmental challenge, population challenge, and say really at the end is how we can address the energy demand economically, and also without damaging the environment. So this is where the solar energy eventually will play a very important role. If you look at the solar energy incoming to the Earth, on the Earth's surface, we get about 1,000 watt per meter square. And if you multiply by the cross-section area of the Earth, and that will get you about 10 to the 5th terawatt. And we said before, the demand is, in the 2050, the energy demand is about 25 to 30 terawatt. So you can say, if we can convert the solar energy, a small fraction of the solar energy, into electricity, and we'll be able to, and other forms of energy will be able to meet our future energy demand. But of course, here the challenge is the cost, because the fossil fuels are very cheap. For example, electricity generation by coals is about 5 cents per kilowatt hour. So how we can develop the energy conversion technology from the solar energy into electricity at a low cost is crucial for, say, the usage of the solar energy. So if we look at what are the current way of converting the solar energy into electricity, there are two well-established ways. One is photovoltaic cells, solar cells, that people put on rooftop or put on the solar farms. And in this case, it's a solid-state device. It's using semiconductor. Most common is silicon, the same material that we use to build computer chips. And what this device does is a photon comes in, and that's the light. That's quanta of light. And they excite the electron from a lower level to a higher level. And then you extract the electron out by the electrode. So it's a solid state, and the advantage is that you can put on rooftops as well as into large-scale solar farm. The other is solar thermomechanical. So this is essentially using the sun as the heat and generate steam, and using the steam to drive the steam turbine. And with that, we come to the mechanical domain of converting heat into electricity. And this is what's currently done in all fossil fuel plant, using the thermomechanical engines. And of course, the challenge with the thermomechanical is that it's very efficient when you do large scale. So solar thermomechanical is only used in the power plant form. And you use it in big area. You collect a lot of the sunlight and generate steam and power the plant. And for both of those technologies, of course, efficiency is very important, and cost is very important. So I want to spend a few slides to explain why the efficiency is hard to get to the high efficiency. And this is a chart showing the efficiency of different technologies. And the thermal power plant, that's a fossil plant. And a typical one burn coal is about 40 to 42, 43%. If you burn natural gas, drive steam turbine, and the highest can reach about 60%. And the automobile we drive is only about 20% efficiency. So we're throwing a lot of energy as heat. And solar cells is typical silicon-based solar cell is about 15 to 20% range. And then later on, I'll show there are some other cells that has a higher efficiency, 40% efficiency, but that's very expensive. So all those energy conversion is from heat to electricity is here we plot the temperature, and there's an upper limit that's called a Carnot cycle, Carnot efficiency. This is the maximum you can get with any heat engine. And that's also is the basic second law of thermodynamics. And of course, we have other, say, energy form where it doesn't involve heat, like a hydro plant and wind. All this do not involve heat, so it's not subject to the second law there. And I want to here go a little bit into the limit of the energy conversion and why there's this upper limit, right? So any of those heat engines, so this is a generic heat engine. So basically, we take heat in, and we want to get it work, in this case, electricity out. But the problem is you cannot convert all the heat into work. Heat is less, say work is superior, heat is inferior to work. And we have to reject some of this heat to the lower temperature. And this is say, of course, the first law of thermodynamics tells energy balance, what's the heat in, what's the heat going out, and the difference is the amount of work or the electricity you can extract. But why you have to reject the heat? This is the heat is usually considered random. There are random components inside. And work is very ordered, right? That random component, in scientific terminology, we measure it by entropy. So this entropy carried by heat, when you take heat from a high temperature source, and the work cannot take it out. So it has to go somewhere. You cannot destroy entropy, say reduce the entropy. You only generate. When you have friction, you generate entropy. And so at the end, you have to use another heat to take to the lower temperature, reject to lower temperature. And the best you can do is to have the rejected entropy the same as the incoming entropy. So this is the limit. This is why we have to reject some energy. We cannot convert all the heat into useful work. And turns out that this entropy, we typically use symbol S, is related to temperature, and times, say, temperature, it gives us the heat. So with this, you can actually derive under the condition that the best you can do is entropy going to the low temperature reservoir. In this case, it could be a river, it could be the ambient air, that's the low temperature reservoir we typically use. And then you burn fire, so the temperature could be 2,000 degrees, and the environment in absolute temperature is about 300 Kelvin. So that gives you the so-called caloric limit of converting heat into electricity. But the reality is, if you think about if you have the sun, the temperature of the sun is about 6,000 Kelvin, and ambient is only 300 Kelvin. So we should be getting over 90% efficiency. And if you think about we burn fossil fuels, we get about 2,000 Kelvin, and the ambient is only 300 Kelvin. And again, we should be getting over 80–90% efficiency. But we are far below that efficiency. And that's because there are always these long idea factor. So if we take the solar cell, that's the silicon material that people typically use, and put on the rooftop, and see where those energies are really lost, right? And silicon is a semiconductor, and the name of semiconductor means there is a region where no electrons can exist. That's called the band gap. And this band gap is, in the scientific terminology, is about 1 electron volt. So different material have a different band gap, and silicon, the band gap is about 1.1 electron volt. And so when light quanta, that's the photon, comes and meet the semiconductor, it's getting absorbed So that energy is converted, right? The light quanta energy is converted. And what it does is raise an electron from the lower energy to a higher energy. And with that, we want to collect this higher energy electron, and before it fall back to the lower energy. So that's the challenge there. And it turns out it's very hard to collect this high energy electron because there are atoms jiggling in the semiconductor. So they will collide with this electron and quickly release part of this energy to fall into this edge of the, we call it conduction band. And here, what's left behind is an empty hole, and that also fall to the edge. So that means it generates heat. And this part of the heat in solar cell is not useful, and we cannot collect it. So we have, in this process, we lose part of the energy. And it turns out also, even though there's electrons here, there's also empty state that we call hole here. And the difference, we said, is about 1.1 electron volt. And we cannot take all that out. This is the same because this electron carries some entropy. And entropy we have to reject that. So it turns out the workout is less than this band gap. So if I put these three items together, and you will see why we are in a typical solar cell, you get a certain upper efficiency. So this is the sunlight. And sunlight has a wavelength. Each wavelength has a say, corresponding energy and of the photon, the quanta of light. And here, of course, the sunlight peaks about 0.5 micron. That's all eye is sensitive to. And turns out that in the case of silicon solar cell, the energy of those long wavelength photon, they are below this gap, so they cannot raise the electron from here to here. They do not have enough energy. So when we use a solar cell, we immediately throw out this blue part of the energy. And that is about 25%. And then when we raise if the photon energy is here, it's much higher than this band gap energy. So we will lose this part, fast heat, and this is this rest of the blue. So if we look at this is about 80% of this heat is intercepted, and this long wavelength, we cannot intercept it. So this is 80%. And then the gap is about 1 electron volt, and the energy average of this energy is about 1.9. So this 0.9 electron volt is again lossless heat. And then say this 1 electron volt gap, we cannot take all of them. We only take part of them because of entropy. So we only get about 70%. So when you multiply all that together, you have around 30%. And this is the best you can do with a solar cell like made of silicon or other materials. And a single junction solar cell, that's the limit. And this is a historical map. And it comes to one point I want to emphasize when you do research, the efficiency progression. And this is a year by year, and with all the best people in the world doing research on it. And you can see it's making steady progress. And I want to point out if we look at crystalline silicon cell, this one is the line here, right? And the best now is about 26%. And this is in the lab. And when you manufacture them, the best in the deployed world is about 20%. And so silicon is a standard. Over about 90% of the market is made of silicon cells. What's also interesting is this gallium telluride. And cadmium telluride is a thin film. It's cheaper. It's rather than silicon, it's cheaper than silicon. And this is the progression of cad telluride. This is an open circle, yellowish. So you can see here, and it's about 16, 17%. And what's made in the world, say there's U.S. has a lot of solar company had trouble, but the profitable company, one of the two profitable companies, is First Solar. And the First Solar makes the cadmium telluride based solar cell, and their efficiency is actually less than silicon, but they are very profitable because they are cheaper than silicon. So their stock had done reasonable well. I do not look at stock. I don't know what's their current situation. But that tells you one thing: the energy, the cost is essential. And I also want to point out that by pausing here, this is beyond the 30% I mentioned, right? This is a 42%. That's the world record. And in fact, it's very impressive because I said the coal-fired power plant is about 42%, right? The problem is this is not a single junction. It's actually stacking several semiconductor, exotic semiconductor together, and they are very expensive. So it's hard to commercial them economically. And there are people doing concentrate. They try to reduce the cell they use, but say so far there has not been very large successful company based on this multi-junction cells. So another challenge I want to mention is, although I said that a lot of solar, energy, right? We only need a little area, but the problem is the solar energy is very dilute. It's about 1,000 watt per meter square. And so if you think about, sometimes we use a light bulb 100 watt. So per meter square, the total energy come in is only about 10 light bulbs. And so how does that compare to gasoline, right? Gasoline, the energy per kilogram is about 45 megajoule. And if you do your mass, 1 tank of gas is, let's say 50 kilo and 450 megajoule. And I compare 1 meter square solar cell and with a 15% efficiency, and it's only 1 year energy generated is about 2 tanks of gas. That's the energy content. So this is the challenge, because you have to reduce that cost. Otherwise, it's hard for people to buy into the technology. So cost is really essential. And if you look at and the cost is rapidly dropping down. And this is based on per peak watt, and how much is, say, 1 watt of the solar cell installed cost. And you see, look at 2004 compared to 2010. 2004 is about $8 per watt, and 2010 is about $3.5 per watt. And converted into kilowatt hour, if you assume a lifetime of the solar cells, and compare, let's say 20-year lifetime, typically people assumes, and the cost of electricity is about 20 cents per kilowatt hour. And 20 cents a kilowatt hour, I mentioned before, the coal-fired power plant generation cost is about 5-6 cents per kilowatt hour. So about a factor of 3 or factor of 4 in terms of the cost you want to drop. And that's why U.S. Department of Energy, DOE, set a very ambitious goal here, get to $1. So that's a factor of 3.5 drop in the cost. And this is not just the cell itself, it's the frame, everything included. And with that, this technology will be able to compete. And overall, my point is converting solar energy into electricity, cost is essential. Now, I want to turn a little bit on this solar thermal technology. Although, say, first I talked about solar electricity, and the solar thermal is really, there are not many people mention it, but it's actually widely deployed in developing countries. And here is a graph from solar heat or report from International Energy Agency. And this is the deployment of, here is the heat, here is the power. And you can see the solar thermal as heat is in terms of the terawatt hour here is very large. And there are a huge amount of deployment in the solar thermal, particularly like in China where I came, so I grew up. So why this is popular? And this is an interesting example of a solar thermal power plant, solar thermal plant I visited. And this is the production line here. And the production line is used to deposit this coating on glass. And this coating absorbs the solar radiation, but when it's heated up, you do not re-radiate. And so it has a very little heat loss. This is because it has a vacuum. It's a double layer. So you can see the outside is a glass. And here is the glass. And the inner is black. And the black coating is seated on another layer of glass. And here is the seal. And in between is a vacuum tube chamber. And this was a really interesting story because I met a professor who developed it from Tsinghua University. And he was an electronic vacuum tube guy. And during China's Cultural Revolution, he was sent to countryside. And after he came back to Tsinghua University, the vacuum tube was gone. Everybody using solid state electronics. And so he started thinking what he could do with his skills, and he invented this solar hot water tube. It's a vacuum tube. And a typical family installing 1 to 2 meters square cost about $300. So it's very cheap, and it's life-changing. When I grew up, I didn't have hot water. So it was difficult to take a hot shower. And with this, it has changed millions of people's life. And in fact, the installed area here in China alone is 130 million square meter. And that, if you think about the 1 to 2 meters square per family, and this is a 60 to 100 million family household. So it really has changed people's life. And this is where I got some inspiration when we look at can we use this and yet generate electricity, because the solar vacuum tube there is only for hot water. And it's deployed in many households. And my question is, can we generate electricity also cheaply? So that comes to the solid-state thermoelectric effect. And the first one is the Seebeck effect. That's when you have a temperature difference between conductor or semiconductor, one side is hot, the other side is cold, you can measure a voltage. This effect was discovered very, very long time ago, 1821. And people used it in labs to measure temperature. So they call this thermocouple. They put the two materials together and they measure temperature. So this is only as a sensor. And the other is the Peltier effect. And so it's a company, Seebeck. After Seebeck discovered that effect, and Peltier discovered, if these two materials you pass a current, actually one side freeze, the other side heat up. And he could demonstrate you can make ice out of it, even say very early on. So all those effects are called thermoelectric effect. And nowadays, you can actually spend about $10 to buy a module like this. They are made of semiconductor, P and N. And when you pass a current, one side will cool down and the other side will heat up. And the reason is because the charge in the semiconductor, you have P-type, you have N-type. When you pass a current, they go from one side to other, they actually carry heat. So normally, when we pass current through a material, we see there's a resistance, right? We generate heat. But in this case, you actually can create the cooling, and hopefully this will work. You see water plus current becomes ice, right? So there's no compressor, this is a solid state cooling, and here is when you sandwich this device is only about 2 millimeters. It is solid state. So now you can't see it, but here is a piece of copper. Here is a piece of aluminum. I put this in between, and you can see it generates power. So it's a device when you have a temperature difference, you can generate power, and when you pass a current, you can create cooling. And very versatile, but you don't see it in a household, right? If you go to student dorms, they may have one because the small refrigerator actually sometimes are made of those thermoelectric coolers. Or you go to supermarket, you buy a picnic box, sometimes they have a cooler, thermoelectric cooler. And it turns out that the efficiency is not very high because the material characteristics we call the figure of merit is not high. And this figure of merit has electric conductivity. When we pass a current through the material, we don't want to generate heating. That's Joule heating, that's not good. We don't want to generate Joule heating. So we want a very high electrically conductive. And we want this also so-called Seebeck coefficient. That's when you use a thermocouple per degree temperature difference, how much voltage you measure. And then we have in the denominator this thermal conductivity, and we want to be low because if you think about making a refrigerator, this side is cold, this side is hot. And the household refrigerator, you put a thick thermal insulation to isolate the ambient from the cold compartment. And in our case, this is the insulation, the material itself has to be that thermal insulation. So it has to have a good thermal insulator, a good electric conductor, and we want this per degree temperature difference generate a lot of heat, voltage. So that's difficult, and this is where the material research has been very difficult. And since 1950 to 1990, there are not much progress. So those devices were invented, were developed, commercialized in the 1950s, but it really has not gotten into large-scale application because the material performance is not quite there. So we have been working a lot on thermoelectric material. Later on, I'll show a little bit on that. But what I want to demonstrate next is how we can take this to make a generator. So this figure of merit is a material property. And here is the calorie efficiency. And you can see the commercial material is about 1. And in fact, it has a temperature dependence, so it's about here. And if we can improve this, we'll be able to make solid state energy converters. And that's, that can have a lot of applications. So not only just in solar. So now let me come to solar thermoelectric energy conversion. And basically, now we have the idea, if I can create a temperature difference across the solid state material, I'll be able to generate temperature voltage and generate the power. So if you check the history, in fact, this idea was even first patented in 1888. And at the time, they're not, very poor material. And in 1950s, there was an experiment done by Maria Telks, and she demonstrated you can get about 0.6% efficiency. And that was about the same time as solar cell was invented, photovoltaic cell was invented. And the photovoltaic cell win, and that field has, say, steady making progress. And this has stayed as this number for since the 1950s, really low progress. So when we look at this, and the first question is how I'm going to create that temperature difference, right? This is a heat engine, so the larger temperature difference, in theory, the better. And I do a very simple calculation. The heat flow equals this material property we call thermal conductivity, which has a unit about 1 watt-meter Kelvin. And if I want a 100-degree temperature difference, and this is the thickness of that material, L. So I say, okay, if I want 100 degree, if I have a sun, that's the flux from the sun, 1,000 watt per meter square, and I need about 100 millimeter. And this is immediately related to material, the cost, because a lot of material say you won't fly with that. So the K is how I can concentrate the sunlight to get a higher heat flow. And of course, it's easy to say I'm going to use a lens or mirrors or various technology people have been using for solar thermal power plant. But we know that's not going to be cost competitive because based on the material property, I cannot build a solar cell as good as a photovoltaic yet. So I cannot do this big tracking structure with the mirrors, and that's not cost effective. So what we took is this vacuum tube idea. What if I put this device in vacuum? And I have a surface to receive the sunlight, and this is in vacuum, so the heat received has no place to go. They are forced to go along the copper we use and to the material itself. So now I have a piece of metal, aluminum, and copper coated with this absorber, and these are the thermoelectric legs. And I can, if I take this area ratio as my concentration, I call that thermal concentration, then I can do a thermal concentration without the optics, and that way I can potentially reduce the cost. I could also think about some optical concentration, and that's where you have to do your cost balance and to combine them together. So those are some details. It turns out the efficiency is not just due to the materials, but when I raise the temperature of this surface, and I also lose heat. So we have to care about the heat loss, even though it's in vacuum, but when the surface is hot, you will radiate out the heat. So that's why we need those surfaces that can minimize that heat loss. And this is the same even for solar hot water absorbers, collectors. So with that, we have some prediction of efficiency, and it's not say very high with this current material, but it's very respectable because when people look at the solar, anytime you about 5-6%, people start to pay attention because the amorphous silicon solar cell is also just a 6-7% range. So this is a prototype we built. We have this absorber, and then we put the 2 small legs. That's our generator, and then we put it in vacuum. And see the beauty of this is the solar energy absorbed by this absorber. They are flat, but the heat has to go concentrate through this absorber through the leg and create a temperature difference. So this is the efficiency we measure. And here is no optical concentration at all. This is a 1.5 optical concentration, and that's about 5%. So you immediately bring, because I said in 1950s, this efficiency is about 0.6%. So that's a real large step for this technology. And I say this thermal concentration, right? Why it's important? That's because this material we use is a very small amount, right? So I have a big pixel absorber. My generator material is very small. And that way is reducing the cost. And because material cost, with this, we can reduce the material, the generator cost to 10 to 20 cents per watt. So that's the beauty of using this thermal concentration. And this is a vacuum. Vacuum is always a concern. But here is the power output. You can say this is typically what people use in hot water vacuum systems. And even when we are at a higher vacuum, we don't lose much performance. So this is the range of performance. You can see it doesn't lose much until you go to relatively high level of pressure. And this is another interesting aspect. In solar energy, one of the problems is you have climate change. You have clouds. So when cloud comes in, for example, your solar cell immediately, there's no sunlight goes to the surface of the photovoltaic, you're out of electricity. And that turns out to be a big headache. And this is the same for wind. And that's why a lot of times people actually have to build another power plant just beside those renewable power plant to provide the backup leverage. And here is one example where we just switch off the sunlight, and it's a gradual process. That's because the heat is stored, and it cools down. It takes time to cool down. We all have that experience. So in fact, say we can intentionally design and delay that, and we're actually working on how we can do this, potentially do a 24-hour, right? I mean, say this is only minutes, but that's the potential there. So this is the story. In fact, it got a lot of attention from the media, but this is actually for real, because here is I want to say why I'm optimistic. I showed this historical progress of the technology, solar to electrical photovoltaic technology before, and finally we're on the map. And this is a lot of people working on the organic plastic solar cells. And you can see that's in the same range of efficiency. And I mentioned that this first solar, I was in American Physical Society meeting last year. And so this is not their published data. This is when I look at the slide, I just put the eyeball. And what's interesting is I see they are the most profitable solar company. And they started in 2001 with a 6% efficiency. And last year, well, this is 2009, that's the data I have, is about 10% efficiency. And they are very low cost and much lower than silicon, so they made a lot of money. So that's the cost is very important for the success of renewable technology. So in fact, after this, we have a lot of, we actually had a spin-off company, GMZ Energy, and it has very good investors, BP, GE, and Kleiner Perkins. So this is drawing, hopefully we'll be able to put this market in the next year. And what's the future, right? I mean, we talked about this technology, and of course, we want to make it more efficient. And there are different directions, and these are some theoretical calculation. And I mentioned ZT before. Here is about 1. That's our material. So we are doing a lot of material research, trying to improve this figure of merit. And also, we can add some optical concentration. I don't want to add too much because of that related to cost. And I can try to reduce the loss, the emission loss here represented by this epsilon. So there are different ways to go. And also, we are looking at what if I go to higher temperature? right? This is a simulation of putting two materials together, going to higher temperature, and that says potentially when I do two materials together with this object concentration now, and at 100 times the object concentration, I should be able to get about 15% efficiency. And this is, of course, this is only the modeling simulation. There are a lot more work we need to do. And also, when you do this, you have to ask, what's the cost? Can I be eventually competitive? Because as a technology, there are a lot of different approaches, and you have to make them attractive. So here is one slide to show, I do a lot of work in nanotechnology, and the idea we have, this is ZT, how we can improve, is to make actually we fragment the material. So we use a mechanically ball mill, so make a nano powder, and then we recompact them into a bulk form. And there are a lot of interfaces in this material. So even though it's a bulk piece, and there are a lot of interface, and this interface serves as a barrier for the heat flow. It's like a heat is due to the acoustic wave. What do you hear there? We know that when there is a surface, there could be echoes. And if I do a lot of those interface, this high frequency heat waves propagate in the material, say the interface, and they echo back. And with that, we can improve the material, and we have demonstrated in a lot of material systems. And this is a very big effort in our research. But I want to say this is actually very gradual. A lot of people are working on trying to improve those materials because essentially, as I said before, from 1950s to 1990s, there's not much progress in the materials. And then in 1990s, people start thinking about the nano, how we can engineer better using the physics we learned in nanostructures to engineer better materials. And this is one example of what happens if we go to higher temperature, this specific material called sclerudites. And when we go to 500-600 degrees, we get about 10% efficiency. So of course, these are heat engines, the higher temperature, the higher efficiency we'll get. And let me talk a little bit about the other application, because I said solar heat, right? But in fact, if we think about the importance of heat that we encounter every day, we cook, we have our home furnace, right? If you look at the heat problem from two perspectives, one is looking at the efficiency, utilization, right, perspective. The other is looking at the source perspective. And you can see that we're actually losing about 60% of useful energy. We only use 40%. And I said before, color efficiency typically around 80 to 90%. So we are far away from what we could achieve theoretically. So recovering this heat, if we can recover, say, half of this heat, 60%, we really reduce significantly the energy demand and reduce the environmental impact. So that's one view, one way to look at it. And the other is to look at the input side, right? From nuclear to fossil fuel, coals, the natural gas. It turns out that we all use first as a heat, generate heat, drive steam turbine. So over 90% of energy is actually used as heat. So this is where, if we think about the heat, how we can, whether we can use the thermoelectric technology to improve the efficiency of the usage as well as the conversion process. So indeed, there are people looking at various possibilities. And I mentioned, of course, solar thermal. And it turns out big effort now is in the automobiles. because automobile efficiency is only about 20%. And we are throwing out the rest of the energy as heat. And of course, industrial process and home furnace. And roughly, we use about 1/3 of energy for transportation, 1/3 of energy for buildings, and 1/3 energy for industrial process. So everywhere we look, and we can see the opportunities. And heat, for example, in the automobile, and I mentioned it's about 20%. And again, this is about 1/3. And 1/3 of the heat goes through the pipe, exhaust pipe. 1/3 of the energy goes through the radiators. So now a lot of countries have the legislation, particularly Europe, for example. It says that by 2018, if you sell a car, your emission per kilometer driven, your CO2 emission is 1 gram above the standard, you pay €95 fines. So the auto manufacturers are very serious to say to reduce their CO2 emission. That's a policy driven here. But there are many other possibilities. And for example, if we look at the household, right? In your basement, you have the furnace, and it burns fuel, gas or oil, and it creates a 2,000-degree temperature hot source. At the end, we only heat up hot water, right? In a power plant, what it does, it generates steam and drives a steam turbine. But you can't do that easily in a household. So all those solid-state thermoelectric generators could be very useful for those applications. And I can give other examples, industrial waste heat. So it's really we have very big effort in the startup. We have said where we can use this. And because you also, when you have startups, you have to think about the economy, right? And that's the important aspects. So this is one example. If I can use this combined to first take out the energy as electricity before we heat up hot water, I have, again, one stone, two birds situation. So finally, I just want to use one slide to introduce this US Department of Energy Frontier Research Center. And this is a specific solid-state solar thermal energy conversion center that I'm the director. US Department of Energy funded 46 energy frontier research centers. And each of the centers is pursuing a specific topic and focus on the fundamental understanding of energy conversion, energy storage, and energy transport, all those issues. And our center look at how we can tailor the solar energy and use it in the form of heat. So we look at the fundamental science of photon, the sunlight, and convert it into electricity. And then we have to look at the heat aspects, the photon, the lattice, the atom vibrations. And with that, we are looking to create a really transformative technology in thermoelectric and also photovoltaic. And I think with that, I want to acknowledge, turns out that most of the time I'm giving talks, it's really the students and postdocs in the lab. They're working very hard. And also, I want to acknowledge my collaborator. I do not make material. Professor Yang at Boston College makes the material. And this is Professor Dresselhaus at MIT. We have been collaborating. She's a pioneer in this field, very well respected lady. She's an MIT Institute professor. And this year, she got the Fermi Award, a very prestigious award. So it has been a great pleasure working with those people and students. And I want to thank you for your attention and be happy to answer questions.